Hello, everybody, and um, welcome to the first, well, at least a recording of um, the first week's lecture for 98013, Lean, A Practical Introduction. Um, so, firstly, thank you for taking this course, or at least taking the time to um, follow along with the course as we go through this semester. Uh, so, today's lecture is pretty short and quick. We're going to talk a little bit about what Lean is, give a bit of an overview or preview of what to expect through this semester of the class. Um, do some quick introductions of everybody, and also just go over like administrivia kind of stuff um, that I'm required to uh, talk about. Thanks to Stuco. Okay, so let's get started. So what is Lean? Lean is fundamentally just a programming language. It's developed mainly by a guy named Leo de Mora, who's working at Microsoft Research. Uh, it is a programming language with a very expressive type system, and what that means we'll see as we go through the course. Uh, but essentially, the type system lets you can say a lot at the type system, and that's kind of what gives Lean and other languages like it their power. But first and foremost, Lean is designed to um, write theorems and to write proofs of those theorems. That is its main goal. Uh, there have been up to now there have been four different versions of Lean, um, and the first two are kind of relevant, but the third one is currently the stable version, uh, and uh, the reason that the development of Lean 4 was started, um, was primarily because it was so focused on on proving or on writing theorems and on proving those theorems that the fact that it was a programming language almost got too obscured. So Lean 4, which is the currently in development version, um, tries to bring back some of those kind of the programming language side. But um, we're going to be working this semester mostly in Lean 3. Um, because the focus of this course is on using Lean to prove theorems. So um, since the main benefit or feature, I guess, of Lean is its type system, we need to talk about types, like what a type system is, and in particular what a type is, at least within the context of Lean. So if you're familiar with uh, pretty much any modern programming language that has types, uh, types are kind of this uh, description of what a value actually is, or in particular what you can do with a value. So in Lean, types are a completely extrinsic description, and what that means is rather than the type describing like the necessarily describing the shape of a value, or what the value looks like. It instead is describing uh, what you can do with the value. It's kind of external behavior, and we'll see what I mean by that in hopefully today. Uh, and the other important thing to know about types in Lean is that every string of characters that you write in Lean either does not type check for whatever reason. Maybe there's a syntax error. Maybe it actually is a valid expression, but it doesn't type check. Um, or it has a unique type. Um, and the uniqueness of the type is actually important. There are some languages where that's not necessarily true, but in Lean, every value that is well typed has a unique type. And the last bullet point on here, types that the fact that types are themselves values, um, is a fundamental feature of dependently typed languages like Lean, which we'll touch on a tiny bit today. But um, so let's actually just get into it. Let's look at a couple of examples that I have pulled up here. So here I have Visual Studio Code opened a um, with the Lean compiler running on the side here. So we have so I can write certain I can write Lean on the left, and the Lean compiler will kind of respond on the right. Um, this is what gives interactive theorem provers the interactive. So one thing I can do in Lean is to just get the type of an expression. So if I type hashtag check, that's a command that tells the compiler to give me the type of what I write here. So I can write 5, for instance, and Lean happily responds, oh yes, 5 is a natural number. This black blackboard n is short for nat, which is the type of naturals. Similarly, I can do something like check hi, and it says, okay, hi is a string. Very cool. Um, I can do more complicated expressions. So for instance, I can do 5 plus 10, give me what the type is of that. And Lean is like, okay, sure, that's also a natural number. Um, I can, if you're familiar with any like functional programming languages, we can write lambda expressions here. So I can write, a function from uh, x, which is a, a natural number, to um, to just the value x. Uh, and Lean will respond, okay, that's a function from naturals to naturals. Um, Interestingly, you did see me type out this like blackboard n the way that I do that. I mean, if you hover over any sort of like special symbols or anything in Lean, VS Code will show you how to type that. So here I typed it just by like backslash bn, but you can do like backslash nat or whatever to type it. You can also replace, instead of writing fun, you can write backslash fun, or backslash lam also works to write a lambda, and that's equivalent to fun, um, which is why Lean shows it as a lambda over here. Uh, so then there's, to give some examples of things that don't type check, I can write something that's not actually valid syntax. So like for instance, just a single dot is invalid syntax. So Lean will just respond it's invalid expression. Or if I do like a backslash dot or whatever, anything that's not like explicitly something like a valid syntax. Um, or it can try to do something that actually doesn't type check. So if I try to apply this lambda expression from above that takes in nats and returns a nat, if I try to apply that to the string hi, well, that's not going to type check, right? Because we're applying a string to something that is expecting a natural, and that's what Lean says. It says, okay, I expected a string, or sorry, I expected a natural, but you gave me a string. Subtle makes sense, right? Um, the regarding the last bullet point about types themselves being expressions, well, I can take any of these types from above. Let's maybe start with string. So if string is a valid expression, so I can check what its type is in Lean, right? Because every expression has to have is either not well typed or has a unique type. So here I can write the expression string, and it's like, okay, string is a type, and this should make sense, right? So like, um, I don't know what you would expect here, but so string or nat, they all have type, capital T type, which says that they can appear on the right hand side of this whatever has type whatever. Uh, so this all works out, makes sense. Um, well, maybe it doesn't make sense yet, but at least isn't complete nonsense yet. Uh, so the the type system that Lean has, there's actually only two kinds of types. So the first, there are inductive types, which are, if you have taken 150 or are familiar with MLs, it's essentially just an ML data type. So they are recursive algebraic data types. They're actually a lot more powerful than ML data types, but we won't get to that until next week. And then it has function types, which we've already seen. So, take something in, give something out. Um, Lean's function types are dependent function types, which I'll also explain next week, but um, for now you can just think of them as regular functions that just take some input and give some output. Um, So actually, let me give an example real fast of. Well, so for instance, one of the classic kind of things that we would, uh, one of the classic examples of a data type is just like natural numbers, right? So in ML, we would write something like data type nat is equal to it's either 0 or the successor of a natural number, right? This is like a valid ML data type. And the natural numbers in Lean are defined exactly the same way. If I actually like alt click on this nat, it'll bring me to the definition in Lean's standard library. And here's the definition of nat. It says, okay, nat is an inductive data type, which is either 0 or the successor of a natural number. I know the syntax is weird. There's a lot going on here, but you should be able to see kind of the rough structure. So we have these kinds of inductive data types. We can also, write recursive functions. Like, right, that's the the elimination form of inductive types. It's the thing you can do with inductive types is we can recurse on them. So another classic example, like Fibonacci numbers, I can define those real fast as a function that goes from natural numbers to natural numbers. The syntax is a little bit weird here, but you should be able to follow along. So in the case that the input is 0, we're going to return 0. In the case that the input is 1, we'll return 1. And in the case that the input is some natural number n plus 2, then we're going to return the Fibonacci number of n plus the Fibonacci number n plus 1. So this is pretty much exactly what you would write modulo the syntax in another programming language, in a similar programming language. Um, so that's all works as you'd expect. Um, so the place where um, Lean starts to diverge from other like functional programming languages and similar is that uh, it's primarily designed to do math proofs with, right? So um, the way that we do that in Lean is via this correspondence called the Curry-Howard correspondence, or sometimes the Curry-Howard Lambek correspondence. Um, and this is a informal kind of theorem, you might think of it as, that uh, essentially just says, given a proposition, any sort of like logical proposition P, something that you can, prove in math, some statement that you can prove in math. Um, you can express that statement as a type in in the type system that Lean implements. um, so you can express that proposition as a type, and then and here's kind of the kicker: the proposition that you've stated is true, or more accurately, is provable, if and only if there exists some expression in the programming language that you're using which has that corresponding type. So, for instance, the proposition P implies P. Um, we can translate that into a type, and then the proposition P implies P is only true if we can come up with some value such that it has type like P implies P, or whatever the type is that corresponds to P implies P. Um, and that's how we're going to actually do like mathematical proofs in Lean. I actually have a couple examples that I can go through of doing exactly that. So for instance, um, let's say we want to prove the like theorem that P implies Q implies P. So throw back to concepts. This is a true proposition. If you know that P is true, then no matter what Q is, P is still true. And we can implement this as a theorem, uh, which I'll call axiom one. And we can say that for any like proposition P, this syntax is all new, but um, try to kind of guess what I'm saying. So for any proposition P and any proposition Q, uh, we can just write P implies Q implies P. Um, so this is a type. I can actually if I go to if I go down here and I write like check um, check P implies Q implies P, it would say that it has type. So this is just a type, but it also is kind of a proposition. It's a statement of this proposition P implies Q implies P. And in order to prove it, we need to provide a value that has that type. And the in particular the type here, or the expression here that has that type is just like a nested lambda expression where we take in P, we take in Q, and then we return P. Or rather, we take in a proof of P, uh, and then a proof of Q, and then return a proof of P. Um, the way that I like to read this is that, give me a proof of P, which I'll call lowercase p. Give me a proof of Q, which I'll call lowercase q. Then I will give you a proof of P, which is lowercase p here. Uh, and that's kind of that is the correspondence, right? We've stated a mathematical theorem, and then we've proven it by giving a value that has this type. Maybe more, maybe less confusingly, I can also just write theorems like, or I have to write an example here, but I can write, theorems like 5 plus 5 is equal to 10, which we know is a true fact. And I should just be able to, yeah, so like Lean can automatically generate a proof that 5 plus 5 is equal to 10. So this is a type here. This 5 plus 5 equals 10. This is actually a type. And Lean is generating a value which has the type 5 plus 5 equals 10. But it is just, again, a type and a value that we're using to state this theorem. More and another weird thing, now that we're kind of like conflating programs with proofs and all of this stuff, we can also do like proofs about programs. So for instance, I can write as a theorem, I can say something like, Fibonacci, the Fibonacci numbers always increase, or at least never decrease, I should say. So we would want to kind of state that as like, for all natural numbers n, that Fibonacci function that we just defined, the Fibonacci function applied to n is like less than or equal to the n plus 1th Fibonacci number. Why is this not typing for all? There we go. So this is a theorem statement. This is a proposition that we could try to prove. But in Lean, it's just a type. This entire expression is just a type. And then we can, build an expression to prove it. This one's a little bit more complicated than the last one. Lean can't just automatically generate a proof. I need to give it a little bit of structure. But here's the weird thing. Lean lets you kind of generate these values that have these types by essentially saying what you would do in like an informal math proof. So if I introduce the value of n, then I case on that value. Well, then I can now I can Lean has enough information now to actually prove these automatically. So if we look on the right hand side, Lean will even tell us like what it needs to prove. So it says, okay, I need to prove that the Fibonacci number of 0, the 0th Fibonacci number is less than the first Fibonacci number, which is easy to prove, and that the Fibonacci number of like n plus 1 is less than the Fibonacci number of n plus 2. So those are 2 cases it has to prove. And I can actually just ask it to prove that exactly. It'll give me like the entire proof that I need. for both of these goals. Um, but yeah, so that's a couple of just examples of lean, how you or demonstrating that you can uh, express kind of any theorem that you want to express, any mathematical theorem you want to express, um, just by um, I don't know why this is not compiling, but you can express any theorem that you want to express as a type in lean, and then generate some value uh, that has that type, and that value acts as a proof of the theorem. Um, so yeah, uh, kind of overall, what to expect from this course. There's you know, the the goal of this course is kind of to help you learn how to actually build all of this mathematics on top of the type system that Lean gives you. Uh, there are a lot of kind of special or specific techniques and standard ways that you express the mathematics in the types. And this course, the goal of this course is to teach you that. The issue is that for most real math or the kind of math that you'd actually want to be doing, there's way too many levels of abstraction between the types in the mathematics. It requires a lot of building up to get between the two. So my plan for the semester is essentially uh, in these kind of lecture type things, we're going to be working bottom up, and we'll kind of talk about, what is the type system of Lean? What are the tools that Lean provides us as a programming language, really? And then in the assignments that we'll be doing in like the second part of each class, and that you kind of are going to be finishing at home and stuff. Uh, all of those assignments are working the top down, where we say, okay, here's some of the actual some actual math, and let's try to express that math in Lean and work from the top down and kind of figure out the tools that you need as you go instead of learning all of the tools that you have. And hopefully by the end of the semester we kind of meet in the middle between those two, uh, so that you're able to actually do math in Lean. Um, so yeah, uh, at this point in class we kind of went around and did introductions. Um, and if you weren't in class, I would still love to know this information. Uh, Basically, what's your name? What's your year and major? And what are your interests in math and theoretical computer science? The reason I'm asking for your interests in those fields is essentially that I am going to be designing problems to that for I'm going to be designing problems as like practice for translating different mathematical theorems into types in Lean in a few weeks. So I kind of want to know what fields to pull those problems from, so everybody has something to to pick that they actually like. Um, so yeah, let me know what you're interested in, and I can kind of tailor the problems to that. But yeah, if you weren't in class, you can just answer these questions in the introductions channel in our Discord server, and that is still super helpful to me. Um, so from here on out, mostly just administrative stuff. Um, so in terms of attendance, you just have to tell me that you're not going to be here uh, before class. Um, I don't care what the reason is, as long as you just tell me beforehand. All of these lectures will be recorded, so you can just watch the lecture portion after class. But it is a lot more fun if you come to class, especially for the actual assignments, because um, a lot of the assignments, especially as we move through the course, are going to get pretty hard, and it makes it much easier if you're working in a group or with other people, and much more fun. So please come to class, basically. um, so Stuco also requires that I uh, give you all grades to some extent, or like some system for pass fail. Uh, and I think that grades are dumb. So my system is basically uh, if you complete the first two assignments of the course, which is basically like the first 5 weeks or 4 weeks of the course, then you will pass. That's it. Uh, um, the and I like I my only expectation for every assignment this semester is just like to show some effort or to like you know complete it to some vaguely acceptable level. I have very low standards, so yeah, take that for what you will. I am going to be giving more individualized, meaningful feedback for some of the assignments when it's more like when I feel like it's necessary or helpful. Um, but they won't at all affect your like whether you pass or not. The only things that affect your whether you pass is just finishing the first two assignments. Okay. Um, in terms of deadlines, I'm very flexible. I really don't care when you hand stuff in. I've I do have a schedule laid out in the syllabus for like kind of when I expect you to be done all these assignments, and I have allotted hopefully more time than you need to do any assignment. um, like most of these assignments, you should be able to finish all of these assignments by the time that I expect you to finish, even just working in class. Like you don't need to work outside of class, um, because we have quite a bit of time together every week. So do try to stay on schedule. If you do find yourself falling behind for whatever reason, maybe you have a really hard or busy semester, that's perfectly fine. I just need the first two assignments by the end of the semester, and I'll pass you. Um, because my goal is just for you to learn like something from this course. So that's all. That's all I need from you. Um, but I do need those by the end of the semester, I guess. Like I'm not gonna take them after this. I can't take them after this end of the semester. uh, Collaboration wise, please collaborate. You can collaborate on any assignment, the first two included. I don't care. Um, it is very helpful, in particular with Lean. Uh, Lean, it is hard to write code in Lean, speaking from experience. So working in a group or doing some sort of pair programming is definitely the way to go. Um, if you have questions, like the first people that you ask should be your other students, the people around you, um, because you will have a lot of questions, and it is okay to have a lot of questions, but it does make everything easier if you ask each other first before coming to me. Obviously, if you guys don't know, like come to me, um, but your first resource should be each other as you guys are learning together. Um, when we get to like the kind of so the second half of this course is mostly dedicated to like a kind of final project, if you will, but it's like 6 or 7 weeks long, so I don't even know if I can call it a final project. Uh, Dedicated to some project that you are basically just trying to start a formalization for whatever like whatever theorem you want or whatever problem you want. And I do have like slightly higher expectations for if you're working in a group than if you're working alone. Uh, I kind of expect two people to be able to do more than I would expect one person to be able to do, but again, I have very low expectations, and also it doesn't count for grades or anything. So like, take that for what you will. Okay. Um, yeah, I think that's it. So the rest of the time that we spent in class was dedicated to the natural numbers game, which is the first assignment of the semester. Um, I planned for this to take like 3 weeks to, for you guys to finish. Uh, it shouldn't take you that long, hopefully. But it's a super fun introduction to programming in Lean that kind of introduces you to some of the it goes from the top down, and you're doing kind of the you're trying to do math on natural numbers in Lean, but it is a really helpful introduction and hopefully kind of shows you the power of Lean. So yeah, my only requirement is basically that you uh, get most of the way through the natural numbers game. Um, it should save your progress as you if it should save your progress even if you exit the tab. It's like an online kind of thing. Let me pull it up real fast. Um, but yeah, so it's formatted as like a kind of textbook thing with exercises built in. The text is super useful and will teach you a lot of stuff better than I can. Uh, and the games are the kind of like uh, puzzles are really fun and very guided. If you have any questions, please feel free to ask or like send a question in the Discord server or whatever works for you. Um, but yeah, I think that's everything. Um, so yeah, I'll see everybody in class on Thursday or next Thursday, and until then, um, see y'all.